In the steppe of northern Kazakhstan, there's a chimney taller than the Eiffel Tower. It serves a power plant in a city most people will never visit. And here's the part that should bother you. That chimney doesn't remove a single gram of pollution. Not one. It was built at staggering cost to do something that sounds almost backwards. To take the dirty air coming out of the plant and throw it as high into the sky as physically possible. Not to clean the smoke, to lose it. So here's a strange question. Why would anyone spend a fortune building the tallest structure for miles around just to move a problem instead of fixing it? That's not an oversight. It's one of the oldest bets in engineering. A bet we've been quietly making with the sky for about 200 years. And every so often, the sky calls the bluff. Let's get one uncomfortable thing out of the way early. We cannot stop putting stuff into the air. Not because we're careless, because of physics. Almost everything that powers a modern life involves burning something, or heating something, or reacting something. And when you do that, you don't just get the thing you wanted: heat, electricity, steel, cement. You also get a list of leftovers nobody ordered. Sulfur dioxide, nitrogen oxides, fine particles small enough to slip past everything your lungs use to defend themselves. Carbon monoxide, a whole catalog of compounds with names that don't fit on a thumbnail. So the engineer's job was never make pollution stop. That's not on the table. The job is quieter and harder than that. Given that we're going to make a mess, where does it go, and who breathes it? This is about the most visible answer humans ever came up with: the smokestack. A piece of infrastructure so ordinary you've stopped seeing it. And underneath that boring gray tube is a genuinely clever idea, a genuinely dangerous assumption, and at least one disaster that changed the rules forever. Let's start with the clever part, because honestly, it's beautiful. Light a candle, watch the smoke. It rises. You know why. Hot air is lighter than cold air, so it floats up through the colder stuff around it. Buoyancy. Toddlers understand this. Now here's the move. Put that hot rising air inside a tall vertical pipe, and something disproportionate happens. The pipe doesn't just hold the rising air, it amplifies it. To see why, forget smoke for a second and think about water. Dive into a pool, and the deeper you go, the more pressure you feel, because there's more water stacked above you, pressing down. Air does the exact same thing. It's just so light you don't notice. Climb a tall building and the pressure drops a tiny bit. There's slightly less air piled on top of you. Now picture two columns of air, side by side, same height. One is the cold air outside the chimney. The other is the hot air inside it. They start at the same pressure at the bottom, but hot air is less dense. It's lighter per meter. So as you go up, the pressure inside the chimney drops slower than the pressure outside. By the time you reach the top, the inside is at a noticeably lower pressure than the outside at the bottom. And nature hates that. Higher pressure shoves toward lower pressure, so air gets pulled up and out of the stack, which pulls fresh air in at the bottom, which feeds the fire, which makes more hot air. It's a pump with no motor, no fan, no electricity, no moving parts. Just a tall pipe and the difference between hot and cold. Engineers call it the stack effect, and it gives the designer exactly two knobs to turn. Make the gas hotter, or make the stack taller. Either one increases the draft. Taller is the one you can see from the highway. So far, so elegant. Now here's the twist that I love. Picture a 19th century industrial city. A forest of brick chimneys, sky the color of a bruise. If I asked you why those chimneys were tall, you'd probably say, to carry the smoke up and away from the people. To protect the air. Wrong. Almost the opposite. Those stacks were tall because tall stacks made the fires burn better. Remember the pump? More draft means more air pulled through the furnace. Means hotter, more complete combustion. Means more useful work out of the same coal. The chimney was a performance part. An efficiency upgrade. Cleaner city air? That was an accident. A side effect nobody was optimizing for. If the smoke happened to end up over the next town instead of this one, well, problem solved as far as anyone cared. Then the technology moved on. Electric and diesel motors let us blow air through furnaces with fans, so we didn't need a giant pipe to make the fire breathe anymore. By rights, the great chimneys should have vanished. They didn't. Because right as the original reason for tall stacks died, a brand new reason was born. The accident became the assignment. That happy little side effect, pushing smoke up and away, got promoted to the entire point. As governments started writing rules about what people were allowed to breathe, engineers reached for the oldest trick they had. And they wrapped it in a slogan that's been repeated for a century. The solution to pollution is dilution. Which is true, right up until the moment it's catastrophically fatally false. Here's the assumption hiding inside every tall stack. The idea is, lift the pollution high enough, let the wind spread it thin, and by the time it drifts back down to where people are breathing, it's so diluted it can't hurt anyone. Many of the nastiest pollutants don't last forever. They react, they break down, they fade. Spread them thin enough for long enough, and the air heals. For that to work, you need the sky to do its job. to keep mixing, keep diluting, keep carrying things up and away. The terrifying truth is that the sky doesn't always cooperate. Normally, air gets colder the higher you go, roughly 10 degrees Celsius cooler for every kilometer up. That's why mountaintops have snow, and that gradient is what lets hot smoke keep rising. It's always warmer than the air above it, so it keeps floating, keeps climbing, keeps spreading. But sometimes the atmosphere flips. You get a layer of warm air sitting on top of cooler air near the ground. It's called a temperature inversion, and it's not exotic. It can happen on a cold, still morning when the ground chills the air right above it. And that warm layer acts like a lid. Your beautiful buoyant plume rises, hits the lid, and stops. It can't punch through. So instead of climbing into all that open sky and thinning out to nothing, it spreads sideways. It pools. It accumulates. The pump still works, the pollution still comes out, the sky just locked the exit. Engineers actually have names for what plumes do under different conditions: coning, looping, fanning, lofting. But there's one that's the nightmare. It's called fumigation. It's when there's a lid up high, churning unstable air down low, and the plume gets trapped and stirred straight back down into the streets where people live. That's not a diagram. That has a body count. October 1948. Donora, Pennsylvania. A small mill town in a river valley full of steel and zinc works pouring out smoke the way they did every single day. Then a temperature inversion settled over the valley and didn't leave. The lid came down. The smoke had nowhere to go. For days, the pollution the town produced every day just stayed, piled up, thickened until people couldn't see across the street. By the time it lifted, around 20 people were dead and thousands were sick in a town of about 14,000. Nearly half the population fell ill from the air they'd been breathing without a second thought their whole lives. 4 years later, the same physics hit London on a scale that's hard to comprehend. December 1952. A cold snap, everyone burning coal to stay warm, and an inversion clamped over the entire city. The Great Smog. Estimates of the dead run into the thousands, and later analysis pushed that number far higher. People died in their homes from the air inside a major modern city. This is the moment the bet stops being abstract. Dilution is the solution, assumes the sky is an infinite room with the windows always open. Donora and London prove the windows can slam shut, and when they do, the height of your chimney doesn't save you, because the lid is below the level you were counting on to carry everything away. So the obvious fix is, build taller. Build above the lid. And for a while, that's exactly what we did, which is how the cure became a different disease. Through the 1960s and 70s, stacks got tall. Genuinely, record-breakingly tall. The logic was airtight on paper. Punch the pollution up so high that no inversion, no calm day, no valley could ever trap it near the ground. Protect the people downwind. Pass the local air quality test. It worked. The air right around the plants got better. The test was passed. But the pollution didn't disappear when it left the top of the stack. Of course it didn't. Sulfur dioxide lifted hundreds of meters into fast upper winds doesn't vanish, it travels. For hundreds of kilometers. Across state lines, across national borders. And up there, given time and altitude and moisture, that sulfur reacts. It turns into acid. And it comes back down, not as a poison cloud over the plant that made it, but as acid rain falling on forests and lakes in places that had nothing to do with it. Read that back. The tall stack didn't reduce the pollution. It exported it. It took a local problem you could measure and turned it into a regional problem someone else inherited. Often someone with no power plant, no vote, and no warning. That's the whole trap of dilution, laid bare. Height doesn't destroy anything. Height relocates. It buys clean air directly above the smokestack by quietly writing a check that lands somewhere over the horizon. The engineering was sound. The accounting was a lie. So we come back to that chimney in Kazakhstan, taller than the Eiffel Tower, removing nothing. Now you can see it for what it is. Not a cleaning device, a displacement device, a monument to a beautifully simple idea. Lift the mess, let the sky take it, and to the slow, painful discovery that the sky has limits and a memory and an address it eventually delivers everything back to. Here's the insight worth keeping. The real engineering of clean air was never the stack. The stack is the easy part. It's a tall pipe and some honest physics. The hard part was admitting that the tall pipe is a last resort, not a solution. That the smart move is to never let the bad stuff out in the first place. That's why modern plants are wrapped in expensive machinery you never see from the road. Devices that pull the sulfur out, trap the particles, break down the nitrogen oxides at the source before any of it reaches the chimney. Those systems can cost a serious fraction of the entire plant. They are not glamorous. Nobody photographs them. And here's the detail that tells you the lesson actually landed. The rules were eventually rewritten, so you can only get so much credit for building a taller stack. You're not allowed to dilute your way out of cleaning up. Height stopped being an excuse. Because the whole game finally got named correctly. The goal was never to move the pollution somewhere we can't see it. The goal is for it to not be there at all. The next time you pass a smokestack, and once you start noticing them, they're everywhere. Look at how tall it is. That height is a confession. Every meter is the height of a problem we couldn't fully solve, written in steel and concrete and left standing in plain sight. The taller the stack, the bigger the bet that the sky would just take it. For 2 centuries, we treated the air over our heads like an infinite room with the windows always open. It was the one place big enough to lose anything in. A whole atmosphere. Surely you couldn't fill that. But the sky was never a room. It was always a system, with moods and lids and limits, that hands back everything you give it. The cleverest thing we ever did wasn't building the chimney. It was finally looking up and realizing the ceiling was never as high as we hoped.